In this video, we learn about the double integrals where the limits of x and y are not directly given to us. So let us look at the following problem. We want to evaluate the following double integral where r is bounded by y equals to 0. So y equals to 0 is the origin. We also have y equals to x squared. Then y equals to x squared is a parabolic function, and y equals to 4. Y equals to 4 is the line that cuts y at 4. So we also have the function f of xy equals to x y squared. When we check here, this function xy squared will be used to replace the following part which we have here. So we also have dA. What is dA? dA is nothing but will be used to represent dx, dy, or dy, dx, depending on how we have arranged our limits of integration. So let us try to fit what we have into the following in double integral. We have f of xy. F of xy is given by xy squared. So we have xy squared dA as it is for now, because we don't know whether we must have dx first or we must have dy first. Let's just keep it as dA. And then we have the function y equals to x squared, also the line y equals to 4. Out of the two, we can find the point of intersection. As we can see that y and y, the two are equal. So finding the point of intersection, we must have x squared equals to 4. So since we have x squared equals to 4, we can take the square root both sides. By taking the square root both sides, we must have x equals to plus or minus 4 like this. And then now we have x equals to plus or minus 4. Let us find the values of y when we have x as positive and negative 2. So if x is positive 2, we substitute positive 2 in this equation. We can clearly see that y is a 4. And then if x is negative, substituting negative 2 in this function, y will also give us a 4. And then it follows that when x is negative 2, y is a 4. Again, when x is positive 2, y is a 4. Then from what we have here, we can draw the graphs. So let us draw the graphs. Then let me draw the graph from here. So this is the origin. Let me say now this is the line x equals to minus 2, or the point x equals to minus 2. Then the point x equals to positive 2. We have the line y equals to 4. This is the line y is equal to 4. So when x is negative 2, y is a 4. Also when x is positive 2, y is a 4. So it's a parabolic function. Then it ends at the point 0. So we'll have the following smooth curve. Then this is how the graph will go. Then this is the graph of y equals to x squared. Then we can shade this part here. Yeah, all right. So this is what we have right now. You need to listen to me very careful. We have the following xy squared. So we have the limit. Check x start from minus 2 up to 2. We consider only this part. So we can say x will start from minus 2 up to positive 2. Now we're done with the parameters of x. So we want to find the parameters of y from the point, this one, up to this one. How then can we determine the parameters of y? Let us check. From this point, as we move from the left to the right, you can see that the line y equals to 4 is above the parabolic function. As we move to the right, the line y equals to 4 is above the parabolic function. So we can say that y will start from x squared up to 4. Now we have the limits. So let us try to fit in the limits into the double integrals. We have minus 2 and 2, which are numerical values. Numerical values, always try to put them in the outside integral. So we have minus 2 and 2. This will make our life easier when integrating this problem. Alright, so let us move. We have y running from x squared up to 4. The lower limit is x squared and the upper limit is a 4. So now listen to this. Because in the outside integral we have the limits of x, it means this side here, or in the outside, we must also have dx. And then in the inside integral we have the limits of y, which runs from x squared up to positive 2, positive 4 I mean. Then we can see that we must have dy, then in the outside dx. Once we have this, then we are done with the problem. All we have to do is to integrate from the inside to the outside. Check the problem step by step. So this is the inside part, and then this one is the outside part. So starting from the inside, this is what we have: xy squared dy. What do you need to do from now on is to integrate xy squared with respect to y. By integrating this part with respect to y, we get xy to the third over 3. The limits starting from x squared to 4. Because we have integrated with respect to y, it means now where there is y, we have to substitute our limits. So let us have the following. We must have x instead of y. Our substitute the value of 4. We have 4 to the third over 3 minus the lower limits x, or instead of y, I'll substitute x squared to the third over 3, like that. This is equal to x 4 to the power 3, 4 to the power 3, this is 64. So we'll have 64. So it means we'll have 64x over 3 minus, then we have 2 times 3. 2 times 3 is a 6, plus 1 is a 7, which follows that we'll have x to the power 7 over 3. Then this expression which we have here will be used to represent the inside part of our double integral. So it follows that what we have right now is minus 2 up to 2. Instead of this part, now we must have the following expression. Then I will have 64 x over 3 minus x to the 7 over 3. So we represent this information, we replace this information by this expression, and then dx. You see, this is what we have right now. And then we can see that from this we have 1 over 3, 1 over 3, and then 1 over 3 is common. Let us take it out. Then we'll take it out, it becomes the coefficient of our integral. We have minus 2 up to 2, then 64 x minus x to the power 7 dx will remain. So let us move. What we have right now is 1 over 3, and then when we integrate with respect to x, so we'll have 64 x squared over 2 minus x to the power 7, must have 7 plus 1, this will give us 8 over 8. The limits, they run from minus 2 up to positive 2, as you can see. And then what is this? This is nothing but 1 over 3. 64 over 2 is 32. X squared minus 1 over 8, x to the 8th minus 2 to positive 2. Alright, so all we have to do, because we're integrating with respect to x, where there is x, now we have to substitute our numerical values. 1 over 3. So instead of x, I will have 2. So we must have 32. And then 2 to the power 2 is a 4 minus 1 over 8. And then instead of an x, I will have 2. And then I will have 2 to the power 8. 2 to the power 8 is 256. And then I will have 256 like this, alright. And then minus the lower limit So the lower limit is 32. Instead of positive x, I'll have negative 2. So this is the same as negative 2 squared is a 4. Alright, and then minus 1 over 8. Then negative 2 to the 8th. I think this is the same as what we have. Negative 2 to the 8th is positive 256. 256, like this. So we have 1 over 3, and then 32 times 2 times 4. 32 times 4 is 128, minus 256 over 8. 256 divided by 8, this is 32. Then minus 32 times 4 is the same as 128. Minus times minus will become positive 256 over 8 is positive 32. Alright, so now let us check the problem. We have 128 minus 128. We have minus 32 multiplied by positive 32, which gives us a 0. So what is remaining inside the bracket is a 0. And then what is 1 over 3 multiplied by 0? And the answer that we get is a 0. So this is the complete solution of what we had to evaluate. So we can also look at another problem for the sake of practice. So let me try to look for another problem. Alright, evaluate the following. We have the double integral. This time around we are given the limits starting from 0 to 1, from y to 1, e to the x squared, dx, dy. We want to evaluate the following double integral. So when we check according to the information which we have in the inside, it means we are going to integrate with respect to x, and then in the outside we are going to integrate with respect to y. So let us look at the problem. We have the limit in the inside, we have x. So this tells us that x will run from y to 1, from y to 1, and in the outside we have y. Y will run from 0 to 1, like this. So let us first look at the inside integral. We want to integrate this part, the natural log e to the x squared. So by looking at this particular problem which we have here, it is not easy for us to integrate this part because we don't know the antiderivative of natural log e to the x squared. How then can we solve these particular problems? So for us, in order to solve these particular problems, we need to reverse the limits of integration. So how can we reverse the limits of integration? Let us look at the following information which we have. From what we have here, we can see that we have the line x equals to 1 and the line y equals to x. So this is what we have. So x equals to 1. So let me say this is the point here. X equals to 1. And then the line y equals to x. Then the line y equals to x is this diagonal line. Then from what we have, the limits x starting from y to 1 and we have y starting from 0 to 1. Let us first analyze the limit of x. The limit of x starting from y to 1. So this is what we have here. So remember, this is the line y equals to x. So it follows that x start from this line y up to this point 1. So because that we have used this point to this point, So we are going to shade this side. And then from what we see, you can see that y, they've said that y starts from 0 to 1 according to this limit. This is the point. Y will start from 0 to 1. So what I want us to do right now, I want us to reverse the limits of integration. So by reversing the limit of integration, this is what we'll have. The same diagram. Now I want us to use the x-axis to identify the limits of x or the parameters of x. So let me say now I want x to run from this point to this point, and then from this point to y going up, I want to use the limits of y by changing the limits of integration. So this is what we'll have. It means x now must start from this point 0, this is the point 0, up to the line y equals to x, and then up to the line y equals to x. It means x will start from 0 to y like this. I mean from this point to this point, yeah, x will start from 0 to 1, from this point to this point. So how about y? Let us look at y. From this point we have y as 0, so it means y will start from 0 going up. When we go up, considering this point and this point where the two meet, this is the line y equals to x. So it means y will start from 0 to x. So because now we've changed the limits of integration, let us write them in the double integrals. That means this is what we have. We have x, where x give us the numerical values of 0 and 1. So we've said that in the outside, let us try to make sure that we have the numerical values. So we have 0 and 1, and then y start from 0 to x, 0 to x of the natural log e to the x squared. Because in the inside we have the limits of y, it follows that we must have dy, then in the outside we get our dx. So from now on, all we have to do is to start integrating the double integral from the inside to the outside. So let us integrate this part from 0 to x, e to the x squared dy. What we want to do, we want to integrate this natural log e to the x squared with respect to y. The integral of this part of antiderivative is nothing but e to the power x squared. Then because we integrate with respect to y, we must multiply it by y. So let me put in y to be the coefficient of the natural log e. The limit start from 0 to x. We know that by having the limit starting from 0 to x, and we have integrated with respect to y, it follows that where there is y, we have to substitute our limits. So first I will have the x representing y as the upper limit, e to the x squared, minus where there is y, now I'll put in 0, and 0 multiplied by everything here will just be 0. And then as a final answer, I'm getting xe to the x squared. Then now this part will be used to represent what we have here. So let us have the following. From 0 to 1, instead of this integral, so now I will have x e to the x squared dx. So let us now look at our problem here. When we look at our problem, we can solve this particular problem using your substitution, because all we want to do is to make sure that at the end we cancel this x. So how can we go about solving this problem? So let me say u equals to x squared like this. So then now I differentiate u with respect to x, I'll get 2x dx, and then I divide by 2 both sides, then half du is nothing but x dx. Then we can clearly see from this step that x dx, this is what we have here, x dx, and then it can be represented by half du. So 0 to 1, instead of x dx, I will have half du. This is half. Then where there is e, I will have e. I have said that u is equals to x squared, so I will have u du like this. And then we can take the half or the constant outside to be the coefficient of the integral. Then we'll get 0 to 1 e to the u du like this. And then from the way we see it now, our problem is simple to integrate. So let us integrate the following problem. 1 over 2. So the integral of, or the antiderivative of the natural log e doesn't change. So it will be 1 over e to the u, the limits running from 0 to 1. Because we have integrated with respect to u, it means this time around where there's u, we have to substitute our parameters or our limits. So it follows that we'll have half u e to the 1 is just e minus e to the 0. We know that e to the 0 is nothing but 1. So this is the answer that we get when we solve this particular problem. So I think now you have enjoyed watching this video and you have learned a lot about double integrals, where the parameters of x and y are given, and when you are not given the parameters of x and y. However, the parameters of x and y can be bounded by means of functions. So if you find this video to be useful, so please go and subscribe and like this video. Thank you.